Definition of line vector. If A be any point in space and B any other point, then a directly straight line segment from A to B is called a line vector. Okay, let's put here the space. Here's point A, this is point B. Okay, now a directly straight line segment, the directly straight line segment from A to B is called a line vector, AB. So if you write like this, this represents the line vector from A to B. So AB, let's call a small letter, let's call U here, U. Okay. AB is equal to U. But you see that if you draw a segment, a line segment from B to A, okay, this is minus AB. Now let's draw a line segment from B to A, okay? Here, a line segment from B to A. So here is a vector BA. Now you see the direction from A to B is opposite the direction from B to A. So you write this is minus U, which is equal BA. Okay, so BA is minus U. In general, we always work with a unit vector, which you call EU, such that the magnitude of EU, we call magnitude of EU, is equal to 1. So the magnitude of AB is a pure number, positive, in which AB is equal U times the unit vector. Okay. Now here U, no arrow here, okay, is equal, we call magnitude of AB. Okay, with the size of this line segment. The line segment, the size, is called magnitude. We call here magnitude of the line vector U or AB. You see, it's important. Why? Because AB plus BA is equal to 0. Let's put here. AB plus BA is equal to 0. Why? Because U plus minus U is equal to 0. You see, this algebraic sum, okay, results in a vector. That's why you have to put an arrow on that 0 there. Okay, it's not a scalar. Okay? Suppose you have 5 minus 5. This is 0 as a scalar. In physics and mathematics and engineering, there are a lot of quantities which they require a specification using the line vector, like force, velocity, displacement, and vector field, for instance, in electricity, and others. Likewise, other quantities, they only need to characterize them a number, is a scalar, like temperature, volume, mass, and so on. So vector quantities, to be characterized in physics, engineering, math, they required not only the magnitude, but also the direction. Okay? In space, suppose the magnitude of this vector u is equal to the magnitude of vector v. So magnitude of u is equal to magnitude of v, and they are parallel. We say that u is identical to v. They are parallel, and the magnitude of u is equal to the magnitude of v. In this case, the vector u and vector v, they are perpendicular. So the angle between them is 90 degrees centigrade. They are perpendicular. Here's the case, suppose I have a point P here and point Q here. This is called, this line here, this line, are called a secant line. So this vector here is secant to this curve C. Okay, this is another case. And this one, let's say a vector A and vector B. Vector A and vector B. A and B are collinear, okay? Collinear line vectors. Now, in this case here, consider a curve C in the space. There's a curve. Now, this is a secant line, okay? This line here, the vector here, okay? This is the initial point P, and there's the final point Q. PQ is a vector, we call a secant vector. Now, this line here, this line, touch this curve in only one point P. So this vector here we call tangent vector. Tangent vector. Line vector, okay? Tangent line vector. Because this line here is a tangent line. Tangent line. Because there is only one point of intersection. Here, these 2 points on this line here, the second line, we have 2 points on this curve. Okay? Now, in this case here, we have a plane. Let's call this plane alpha. Now, all these vectors lie in the same plane. So they are called coplanar point, coplanar vector, okay? It's coplanar vectors, because they lie on the same plane. And here is a normal to the plane. You see the difference. And this figure here, n, small n, is normal to the curve, okay? Because it's perpendicular to the tangent vector, okay? N is normal to the curve. His capital N is normal to the plane, alpha. Now, N is perpendicular to any of these vectors lying in the plane alpha. The angle between, for instance, this is a U1, this is a U2, this is a U3, and this is U4. So N is perpendicular to U1, U2, U3, U4, and so on. When this line here is perpendicular to a plane, any vector lying in the plane determine a right angle of 90 degrees with the normal to the plane. Now, suppose a surface S. This is a surface S. So this plane is tangent at point P of the surface. See? Likewise, in this case here, any vector lying on this plane here, alpha, it will be perpendicular to capital N which is normal to this plane, so it will be normal to the surface at point P. And this figure we call skew line vectors. Skew line vectors. Suppose you have two planes in the space with their parallel. This I have a vector u, this I have vector v. You see, this vector and this vector, they are not parallel, necessarily parallel. Let's suppose a vector here. Okay? They are not supposed parallel, and they will never have an intersection point, because this plane, alpha and beta, they are parallel plane. So if a vector v lies in this plane and vector u lies in the alpha plane, they will never have an intersection point. So these are called skew line vectors. Addition and subtraction of line vectors. Suppose someone pulls your arm in this direction and the arm in this direction. They are different direction and different magnitude. Okay, there is an effect, okay, using according to this vector and this vector. The effect is represented geometrically by a parallelogram. So suppose you have a vector A here, this is you are sitting here, and this is vector B. So the parallelogram, okay, is a sum of these two vectors. So is the diagonal of this parallelogram. This magnitude is equal to this magnitude. So here is vector B, and here is vector A. So R is B plus A, okay, or B plus A. So you write here R is equal A plus B, okay. Now suppose I want to add these two vectors here. This is vector u, and this is a vector v. Now I want to add u minus v. Okay. Now this is v. Minus v has opposite direction as v. So minus v is like that here. This is a parallel to this one, okay? And the arrow instead of this in this direction, the arrow will be in this direction. So this is v, okay? This is minus v. So let's add these two vectors, okay? So the diagonal of this parallelogram is like this. So here is the resultant, the sum of u plus minus v. So in this case here, R is equal u minus v is equal u plus minus v. Okay? That's the reason, personally, I don't like adding and subtract line vectors, because you see, if I have a subtraction, I can add and just change the direction of v. So we always add a vector u plus minus v. A plus b plus c. Now, geometrically, you see here that a plus b I called r prime, okay? So r prime is equal A plus B. Now, you see, r prime plus C is just the resultant. So r is r prime plus C. So r is equal r prime plus C. But r prime is A plus B. So A plus B plus C is just the resultant. You see, so if you want to sum several vectors, you just take a common point and take parallel to that, parallel to that, and parallel to that, and parallel to that. Okay? Now, this initial point of the first vector, let's call u1, u2, u3, and u4. You see, the initial point, and this is the final, okay, is the extreme point of the last vector. Just if you adjoin these two, this is my r. Okay. Now, suppose, okay, in this case here, suppose you have a fifth vector, in which is this one here. Okay? Here. This is u5. When you add here u5, you're going to get this. So you close this loop. Okay? This is u5. So you see, the final point, okay, of the last vector coincides with the initial point of the first one. So in this case here, the resultant is equal 0. Okay? Because you're gonna join this point with itself. So the resultant is 0. Consider this case here. I want to add these two vectors, this and this. Okay. Now let's use the parallelogram here, the geometry. Let's make this. Okay? This is my R1, okay, the case 1. Okay? The vector A, the vector B. So R1 is A plus B. Let's call A1 and B1. Now, here is A2 and B2. Look, in this case here, okay, the parallelogram will be like this. This is a parallel, and this is a parallel. So this is my R here. Look. This is my R2, my resultant. And this case here is B3 and A3. Let's use here the parallelogram and the geometry. Look, this is my R3. Now, this case here, we have, you see, the same straight line. You see, the same straight line. Now, the angle between this vector here, let's call A4, and this vector here, let's call B4, the angle is 0 degrees, okay? Now, that's my two arms like that, it's not open like that, so the angle, see, the direction is pointing to you, okay? So this is 0 degrees. Here we add this vector plus this vector. So we have here the resultant will be like this. So this is resultant R4. Okay? That's resultant. In this case here, you have opposite direction. You see, and the magnitude of A is greater than the magnitude of B. So I subtract, okay? It's like this. Somebody is pulling in this direction and another is pulling this direction. Okay, if this vector here, the force, is greater than this, I'm going this side. If this is greater than that, I'm going on the other side. That's the opposite direction. So here I subtract here, it is smaller, I put it over here. Okay, this is my resultant here. This is my resultant. I call R. Let's call R5 and B5. So this is R5. Okay. This here, okay, we have that's the opposite. So the size of B is much greater than the size of A. So if you subtract here, you have my resultant here are 6, you see, goes in this direction because the size of B is greater than the size of A. Okay, in this case here, okay, this case here, the size of A is much greater than the size of B. So you can see from here that the size of the resultant depends on the size of A, the vector A, the size of vector B, and the angle between these two vectors. You see, this is an angle alpha 1. This is angle alpha 2. This is angle alpha 3. This is angle alpha 4, which is 0. This is the angle alpha 5, which is equal 180 degrees, okay, because we have this direction, this direction. Likewise, this one, okay, the angle here, alpha 6, is equal 180 degrees. The magnitude of R depends on the magnitudes of the components of A and B. The components of A and B. Now, and the angle between A and B. Look, let's draw here. This is my vector A. This is my vector B. Okay? So let's draw the sum of A plus B. Okay? Now it's a little bit, let's do this here. Okay? That is parallel. That is B, this is A. Okay? And this is R. R. Okay, look, I will write the letters without the arrow because I want to obtain R in terms of A, B, and alpha. Okay? Now, let's extend this straight line here. And then this is a right triangle. This is alpha. Since this segment is parallel to that, this is B. Okay? And also, this is A and this is A. Okay? This is alpha. Since this B, okay, the direction of this B is the same direction of this. So this is B and this is B. Okay. Now, let's put big letters here. A, let's put here B, C, and let's call B here. A, B, okay? Let's put C here and M here, okay? Now, let's work with a triangle CMB, okay? Now, this is Pythagorean theorem. We can write in this triangle here, we can write. You see, B is hypotenuse here. So B squared, let's write down here. B squared is equal, let's call here M and N, okay? M squared plus N squared. Okay, let's keep this for a while. Now, in this triangle, the big one, A, B, M. Let's apply the same theorem, okay, of Pythagorean here. And A, B, M, okay? The hypotenuse is R squared is equal. Now let's put here AC, okay? It's better for you to see clearly. Let's put here AB squared, okay? AB squared is equal AM squared, AM squared plus MB squared, MB squared. Now, what is AB? AB is R, okay? Now, AM, see, AM is A plus M. So, AM is A plus M, just numbers, okay? Now, what is MB? MB is equal N. Let's substitute here just a letter, okay? Now, we write R squared is equal A plus M squared plus MB squared, so it's N squared. Let's expand this here, A squared plus 2AM plus M squared plus N squared. So, this here, you see, this is N squared. Now, R squared is equal. What is M squared plus N squared? From this triangle here, this is exactly B squared. So let's plug here B squared. So R squared is equal A squared plus B squared plus 2AM. Okay? A squared, this is B squared plus 2AM. Now, from this triangle here, you can see here this triangle. What is M divided by hypotenuse here? M, let's put here. Right now here. M divided by B is equal cosine of alpha. This from this triangle, CMB, okay? CMB, okay? From this triangle we can write here. So M is equal B cosine of alpha. Let's plug M here. So this is equal to A squared plus B squared plus 2AB cosine of alpha. Okay? This is a very, very important result. Now, R is just a square root of the right hand side. Okay? Now, what is important, I would like to emphasize here. Okay, look. A, B, R, and this is magnitude. So it's magnitude, which implies all of them are greater or equal than 0. You see, you don't have magnitude of a vector, a line vector, negative. Okay? What you have, for instance, is a negative vector. For instance, if I have a direction here, suppose I have a unit vector here, let's put EU, okay? EU. And suppose a vector U here. EU is equal the magnitude times the unit vector. What is the unit vector from here? You can see unit vector is the vector divided by its magnitude. That's the definition of unit vector. Now, suppose you have minus U, okay? Minus U is equal the U times minus EU, okay? Because this is a magnitude. This will never be negative, okay? What is minus EU? Minus EU is this, minus EU. Okay? So, the negative here doesn't come from the magnitude. The magnitude is always greater or equal than 0. Okay? That's a very, very important, okay, for you to apply. Okay? Now, A, B, and R, they are magnitude. Magnitude of vector, the resultant is capital R. The magnitude of vector B and vector A, both are A and B. They always greater than 0. But, you see this cosine here? Okay, I will erase here, just for have a space, okay? Let's erase here. Look, the cosine of alpha has sine. Do you remember? Look, here, this is first quadrant, okay? Now alpha on the first quadrant. Cosine of alpha is positive, okay? Cosine alpha is positive. For alpha, okay, between, in this case, okay, alpha is greater than 0 and less than 90 degrees. Less than, I'll erase here, okay? I'll erase, let's put here, okay? Now, for alpha, between 0 and 90 degrees, okay, cosine of alpha, that's for 0 is 1, okay? This cosine of alpha, I guarantee, okay, is positive, okay? Because this axis here, cosine of alpha always goes to the right. Now, if alpha is in the second quadrant, cosine of alpha is negative, okay? So this term here, okay, it has a sign, positive, negative, or 0, not because A and B, but because cosine of alpha, okay? Alpha is 0, cosine of 0 is just 1. So cosine of alpha is 1, so R2 is equal A2 plus B2 plus 2AB. This is equal A plus B squared. So R2 is A plus B squared. Then R is equal square root of A plus B squared, which is A plus B. So if the angle is 0, okay, the resultant is just the sum of the magnitude of each vector. It's the same as this, okay? Look, here is 0 degrees, okay? This is 90 degrees, this is 180 degrees. Now, if it's 0 degrees, if you pull me with a force like that and a force like that, the result is the sum of this force plus this force, because the angle is 0. So that's what we got here. Now, suppose alpha is 90 degrees. Cosine of 90 degrees is 0. So all this term over here, okay, they will come up with 0. So R2 is equal A2 plus B2. This is just, you see, you have A here and B here. This is A and B. This is a rectangle, okay? This is a diagonal of rectangle, so this is R, okay? The magnitude of R, you see R here is hypotenuse. This is A and this is B. So R, this is a right angle. So R squared is equal A squared plus B squared. You see? It's a special case. Now, if the angle is 180 degrees, cosine of 180 is minus 1. So here is minus 2AB. Okay? If the angle is 180 degrees, it's like that. You see? Okay, you have one vector in this direction and another vector in this direction. So the angle between this A and B will be 180. Now, this is minus, okay? Then I have here R squared is equal A squared plus B squared minus 2AB. So this is equal A minus B squared. Now here you have to pay attention. R is equal, look, A minus, see, you take the square root on both sides. R is equal A minus B, let's erase it here, okay, you'll be A minus B if A is equal is greater than b, and will be b minus a if b is greater than a. Why? Why? You see, look, this is magnitude. This is always positive, okay? Now, if this magnitude is greater than b, it's okay. For instance, this is 10, this is 3. So the difference will be 7. It's okay because r is positive, always, the magnitude. Now, suppose a is 3, b is 7. Okay, 3 minus 7, okay, is minus 4. This cannot be possible because r is always positive. So r will be a minus b if a is greater than b. R will be b minus a if b is greater than a. Okay, that's a point just to make it here. Breaking down vector v into components. Okay, the line vectors u, v, and w, when drawn from a common origin, okay, determine a reference frame, okay, a reference frame. There's a reference frame called a base system. Okay? This reference frame is called base system. Now, u, v, and w are linearly independent. Okay. Now, we saw previously that this vector u plus this vector v, okay, end up with the vector called v prime. Okay, this v prime is equal vector u plus vector v. Okay, u and v prime lie in the same plane. Now, you see, u plus v is the same of, in this case, u plus v. Okay, this is also v. Okay, u plus v. This is v prime. Now, let's look v prime and w. Now, v prime plus w. Okay, this is equal. Here's a parallel here. Okay, look, v prime plus w is equal capital V here. Okay, so v is equal v prime plus w plus w. You see, look, v prime, okay, v prime. This is v prime. Look at here. This is parallel here. Okay, look, w plus v prime is equal capital V here. See? Now I will plug v prime right over here. So v is equal u plus v plus w. Now, in terms of the unit vector, EU, E sub u, E sub v, and E sub w, they are unit vector. So I can write here that v is equal the magnitude of this vector u. I call u plus v, ev plus w, ew. Okay, that's why, okay, we break down vector v into 3 components. Okay, so these are unit vector, not necessarily orthogonal. Okay, these are not necessarily orthogonal, but we can also breaking down vector v in this frame here. Look, this is, I call x-axis, y-axis, and z-axis. These are a common origin, and they are orthogonal axes. Okay? Now let's have a vector v here. Let's draw vector v. Now I will break down this vector v into other components. Let's project this vector here. Okay? And here I have my v prime. Attention, this v prime is completely different from this one, okay? Because we are using another reference frame, okay? Now, here's the y-axis. There's a parallel to this line, and this is parallel to that line. So I'll call here xi, here yj. Now, and v prime, okay, from v, okay, I take a parallel line here, okay, this is my vector zk, okay, zk. Look, v prime plus zk is equal v. Now, v prime is equal xi plus yj. See, this vector here, I will break it down in this plane, the plane xy, okay? V prime and xy and yj, they lie on the same plane. Now, you see, this vector here is this vector plus this vector, or this vector plus this vector here. This is the same as this one. And this here is the same as this one. Now, I'm adding v prime to zk. Now, v prime and zk is v. So v is equal v prime plus zk. Okay? Now, this is v prime. So this is also v prime. Okay? Zk plus v prime is equal v. I'll plug v prime over here, so v is equal xi plus yj plus zk. Okay, this is an orthonormal base. You see, this is my unit vector I, here unit vector j, and here unit vector k. ijk, let's write down right here, okay? I will raise here and write down here, okay? ijk, represent a base system, a base. I'll call here standard system. Standard system. They are orthonormal bases. Now these span are 3. This also span are 3, okay, because ijk are linearly independent. Okay, the magnitude of I is equal magnitude of j is equal magnitude of k, and is equal 1. That's why it's called orthonormal base. Ortho because they are perpendicular to each other, and normal because the magnitude of each unit vector is equal to 1. Okay? Now, this is a span that's called a standard system, base system, and they are orthonormal bases. Okay?